Okay, we have a matrix A, and the question is this vector, this 1, 2, 3, 4, 5, 6 by 1 vector in null A? So what it means for a vector to be in the null space of a matrix is that the matrix times the vector equals 0. So my question is, does A times X equal the 0 vector? So A is that, and then my vector X is -7, 1, 1, 3, 1, 0. Okay, so my matrix is 3 by 6, and my vector is 6 by 1. So the inner dimensions are both 6. They match. That means that I can multiply these. So I don't have to stop now. I have to continue on and check and see, do I get the 0 vector? My resulting vector will be a 3 by 1, the outer dimensions. So the inner dimensions have to match. The result is the outer dimensions, 3 by 1. Okay, so 3 rows, 1 column. All right, so first I'm going to multiply row 1 times my vector. So that means you line up corresponding positions, first entry in the row times the first entry in the column, multiply them together, and you're going to do that second entry times second entry, and then you add all the results together. Okay, so 1 times -7 is -7, plus 5 times 1, plus 2 times 1, plus 0 times 3, plus 0 times 1, plus 5 times 0. Okay, so I'm not even going to go, 5 times 0 is 0. Okay, so that is going to give me -7 plus 5 plus 2 is 0. Okay, so now I keep going. Now I'm going to do the second row of my matrix times my vector. So 0 times -7 plus 0 times 1 plus 0 times 1 plus 1 times 3 plus -3 times 1 plus 0 times 0. And that does give me 0. And then third row times the vector, I get -2 times -7 is 14. -10 times 1 is -10. -4 times 1 is -4. 0 times 3, 0 times 1, -9 times 0. And that does give me 0. 14 minus 10 minus 4 is 0. So yes, X is in the null space of A because A times X equals 0. Okay, to find an explicit description of null A, we need to find all the vectors that you can multiply A by and get 0, 0, 0. So I want to solve A times what vectors give me the 0 vector. So this is going to be, try to write this fast. Times what gives 0, 0, 0. So I'm going to augment with 0, 0, 0, row reduce, and see what I get. So this row reduces to 1, 0, 0, 5, 0, 0, 2, 0, 0, 0, 1, 0, 0, -3, 0, 0, 0, 1, augmented with 0, 0, 0. Okay, so this is consistent because I don't have 0 equals a number, and none of my rows translate to 0 equals a number, so it's consistent. So we know there are vectors that can make this true, which I should have known from part A because I have 1 right here. Okay. But because I have free variables, there are infinitely many vectors that can make this equation true. I just have to describe them all, and that would be the null space. Okay, the set of all solutions to this equation is the null space. So I'm just going to describe this solution set by giving a set of vectors that span the null space. So I just want a set of vectors whose span is the solution set. So I'm just going to write down the solution, and then I'll think about how they want me to express it. Okay. So the solution says x1 plus 5x2 plus 2x3 equals 0. And then x4 minus 3x5 equals 0. And x6 equals 0. Okay, so now I have to solve each equation for the pivot in terms of the free variables. So I'm going to highlight my pivots in the reduced version. There's 1, 1, and 1. So those are my pivot entries, the first non-zero entry in each row. So I'm going to solve each equation for the pivot. This is my x1 row, x2, x3, x4, x5, x6. So x1, x4, and x6 are pivots. So solve for the pivots. So I get x1 is negative 5x2 minus 2x3. And x4 is a pivot, so I solve for it, and I get 3x5. And then x6 equals 0, already solved. So if I want to write this in parametric vector form, I would say x1, x2, x3, x4, x5, x6. My solutions look like x1 is in terms of x2 and x3. So let's see, I'm going to need an x2 vector. That's one of my frees. Another free is x3. And another free is x5. So I set it up like this, where I put a vector times each of my free variables. And then x1 is negative 5x2, so I'm going to put a negative 5 here in the x1 position, minus 2x3, so I put a negative 2 there. And there are no x5s in my x1 equation, so I put a 0 there. And then x2 is one of my free variables, so I just want this to say x2 equals x2, so I'm going to put a 1 here and zeros in the other two vectors. x3 is free, so I'm going to put a 0 and a 1 and a 0. x4 is 3 times x5, so I'm going to put a 3 in the fourth entry for the x5 vector and zeros in the other two vectors. x5 is free, so I'm going to have 0, 0, 1. And then x6 is 0, so I'm going to put 0 in the sixth entry in all of my vectors. So this describes the null space. This is a description of the null space. This is every vector, 6-entry vector, where a times x equals 0. You get to choose the free variables, and then you can calculate the pivot variables. They asked us to write it as a set of vectors that span the null space. That would be this set, 1, 2, 3. Those 3 vectors span the null set. So this is another way that we could write this. We could say this equals the span of those 3 vectors. Because remember, the definition of span is the set of all linear combinations, and linear combinations is where you just throw some weights on each vector and add them together. So the way I've written this is as the all linear combinations, which I could just replace with the word span. Now, to give a non-zero vector in null A other than the one from part A, I can pick any vector that's in the span of the 3 vectors we got in part B. So that is, you get to choose the weights, x2, x3, and x5. Choose those weights, put them on the 3 vectors, and you'll get a vector in null A. So let's just choose, well, the easiest one would be 0, 0, 0, right? So I could say -5, 1, 0, 0, 0, 0 times 0 plus -2, 0, 1, 0, 0, 0. So you can see that the 0 vector is always going to be in the null space of a matrix, because you can always choose 0 as your weights. But you could choose any other weights you want and get a vector in null A. Is 13, -2, -25 in the column space of A? So the question is whether or not 13, -2, -25 can be written as a linear combination of the columns of A. That's what col A means. It's the set of all linear combinations of the columns of A. So I'm asking, can you put weights on each of these columns? Are there weights, x1, x2, x3, x4, x5, x6, weights that you can put on those columns that when you add them all together, you get this vector? So I'm going to try to solve for those weights. When I augment with 13, -2, -25. Okay, so this augmented matrix, when I solve, is solving for those 6 unknowns that are my weights that I would put on the columns of A to build 13, -2, -25. Okay, so I've done the row reduction, and this translates to x1 plus 5x2 plus 2x3 equals 8. x4 minus 3x5 equals -2. And x6 equals 1. So there are infinitely many solutions, which means that yes, because there is any solution, 13, -2, -25 is in col A. There are a set of weights, or there is a set of weights that you can put on those columns to get 13, -2, -25. Let's just find one set just to double check. So I'm going to solve each of these for the pivot variable. And then I'm going to choose the free variables. So I'm going to choose the free variables. So let's see, I have x1, x2, x3, x4, x5, x6. So my free variables I get to pick. So I'm going to make them 0 because that's just easy. So my free variables are 2, 3, and 5. So if I make my free variable 0, then I can solve for the pivot variables. Okay, so x1 would be 8 if I'm plugging in 0 for x2 and x3. x4 would be -2, and x6 is 1. So now I'm just going to double check. If I put those weights on the columns of A, let's see, so x1 is 8. So if I do 8 times 1, 0, -2, x2 and x3 are 0, so I have 0 times whatever those columns are. I'll put them in just so we don't lose track. And then x4 is -2 times the fourth column of A, which is 0, 1, 0. x5 is 0. Put that on the fifth column. And x6 is 1. I put that on the sixth column of A. And let's see what we get. So if I just look at the first entries, I'm going to have 8 plus 0 plus 0 plus 0 plus 0 plus 5. And then look at the second entries, and I have 0 plus 0 plus 0, -2 plus 0 plus 0. And then my third entries, I get -16 plus 0 plus 0 plus 0 plus 0 minus 9. And that does come out to 13, -2, -25. So there are some weights. There are weights that you can put on the columns of A to build 13, -2, -25. So the answer is yes. I did a lot more work than was necessary here. As soon as you saw that this was consistent, we could have said yes. There is a solution, which means there are weights. We could have said yes right then. But I just did a little bit more to explain. Okay, now we want to find an explicit description of call A by giving a set of vectors that span the column space of A. Okay, so remember the column space of A is the set of all linear combinations, of the columns of A. And then also remember the word span means the set of all linear combinations. So I could just write call A is the span of the columns of A, right? Span and the set of all linear combinations are synonyms. So I'm just going to put in the columns of A here. Their span builds call A. There we go. Okay. Give a non-zero vector in call A other than 13, -2, -25. Take any weights, throw them on the columns of A, and add them together. Okay, so let's say zeros are the easiest, but maybe I'll change it up this time. Let's see, I'm going to put a 1 on 1, 0, -2, a 2 on 5, 0, -10, a 0 on 2, 0, -4, and a 3 on 0, 1, 0, and then we'll put zeros on the rest. All right, and that will give me, just look at the first entries. So I'm going to have 1 plus 10, and that's it. And then my second entries, I'm going to have 3. That's the only entry I'll have, that's the only term I will have there. And then the third entries, I've got -2 minus 20, and that's it. Okay, so that comes out to 11, 3, -22. And what I chose were these numbers. These were completely random. You could put any ones you want here, and that will give you a vector in call A. Okay, for each set below, Either show that the set is a vector space by writing it as call A or null A for some matrix A, or explain why it is not a vector space. Okay, I think I just realized that I left a question off on the previous page. Okay, so there's a system of equations written here in the set W, which is the set of all 4-entry vectors A, B, C, D, such that this system of equations is true. A minus 2C is 0, 3B plus D is 0. So I'm going to translate that system of equations to an augmented matrix. Okay, so let's see. I have 1, no B's, negative 2 C's, no D's. And then 0 A's, 3 B's, 0 C's, and 1 D. Okay, so that's going to be my matrix A. Because it's equal to the 0 vector, that system of equations, if you solve it, it's going to give you the null space of A, right? Because the definition of null A is the set of all vectors, A, B, C, D, that when you multiply A times them, you get 0, 0. Okay, so null A equals W, which means that this is a vector space. Okay, part B, W is the set of all vectors A, B, C, D, such that A minus 2 equals 0 and 3B plus D is 0. So just looking at this first equation, A minus 2 equals 0, tells me A is 2. A is always 2. No matter what anything else is, we know A is 2, which means that the 0 vector is not an element of W, right? Like 0, 0, 0, 0 is not in W, because every vector in W is going to be 2, something, something, something. A is always 2. So if the 0 vector is not in W, that means W is not a vector space. And just jumping back to A for a minute, if you can write a set as the null space of a matrix or the column space of a matrix, that automatically means it's a vector space, because the null of a matrix and col of a matrix are always vector spaces. Okay, last one. We have a linear transformation T. T goes from the set of all 2x2 matrices as its domain and gets mapped to P2, the codomain of P2. And P2, remember, is the set of all degree 3 or degree 2 or less polynomials. So the rule is you input a matrix A, B, C, D into the transformation T, and the output is going to be AT squared plus BT plus C. All right, the question is, what is the kernel of T? Okay, kernel means the kernel of a linear transformation is like the null space of a matrix. It is the all inputs for T that produce 0 as an output. 0t squared plus 0t plus 0 in this case. So if I want to get 0t squared plus 0t plus 0, A, B, and C, right, all have to be 0. So that means that my matrix that I can input would have to look like 0, 0, 0. But then D has no bearing. So I could put anything here. I'll just call it D. Okay, so the kernel of T is equal to the set of all matrices that look like this, such that D is any real number. And then what is the range of T? So the range, remember, is the set of all outputs of a transformation. So what outputs can I get? AT squared plus BT plus C, where A and B are just real numbers. So my range is P2. I can get every possible degree 2 or less polynomial.